We will now speak about Maxmin strategies. These make particular sense in the context of zero-sum games, but actually are applicable quite to all games. What is a Maxmin strategy? It's simply put a player's strategy that maximizes their payoff, assuming the other player is out to get them. We will concentrate primarily on the two-player case here again, because when we get to zero-sum games, those really make only sense in the case of two players. But keep in mind that one could define this kind of more generally when we speak about Maxmin strategy. So the Maxmin strategy is a strategy that maximizes my worst case outcome, and my Maxmin value or safety level is that payoff that's guaranteed by the Maxmin strategy. And here it is defined formally. The Maxmin strategy for player I is the strategy S1 that maximizes the minimum that the other player, remember that minus I is the player other than I, would hold player 1 down to. And the Maxmin value is defined similarly to be the value of that Maxmin strategy. Now, why would we want to think about the Maxmin strategy? One can think of it either as a simply a sort of a certain cautionary, maybe the other people will make some mistakes and not act in their own best interest. Maybe I'm not sure exactly what their payoffs are. There are a lot of interpretations, or you can simply be paranoid about them and think that they're out to get you. And you know the saying, even the paranoid have enemies. That's the Maxmin strategy. And just to confuse things, we'll also speak about the min-max strategy. The min-max strategy is strategy against, if you wish, the other player in the two-player game, is a strategy that minimizes their payoff on the assumption that they're trying to maximize it. And so here is the formal definition. The min-max strategy for player I, who's playing against the other guy, which we denote by minus I, is the strategy that minimizes the maximum payoff as attempted by the other guy of the payoff to the other guy. And the min-max value is simply the value of that min-max strategy, the value to player 1. Now, why would player 1 want to harm the other guy? Well, you could just be out to get him. That's a possibility. Or they could be playing a zero-sum game, and in a zero-sum game, hurting the other guy is tantamount to improving your own payoff. And so, in the setting of zero-sum games, max-min and min-max strategies make a lot of sense. And in fact, in a very famous theorem due to John von Neumann, it proved that in a zero-sum game, by definition, we consider only two-player such games, any Nash equilibrium, the player receives a payoff that is equal to both his max-min value and his min-max value. And that means that, so we'll call it the value of the game. The value for player 1 is called the value of the game. And that means that the set of Maxmin strategies are really the same as set of the min-max strategies. That is, trying to improve your worst case situation is the same as trying to minimize the other guy's best case situation. And any Maxmin strategy profile or min-max strategy profile, because they're the same, constitute a Nash equilibrium. And furthermore, those are all the Nash equilibria that exist. And so the payoffs in all Nash equilibria is the same, namely the value of the game. One way to get a concrete feel for it is graphically, and here's the game of matching pennies. This is a game where each of us chooses heads and tails with some probability, and if it comes up either if the result of our randomization I end up choosing head and you end up playing tail, you win, and vice versa. Also, if I chose tail and you head, but if we both chose head or both chose tail, I win. And so here are the payoffs. You see here the strategy spaces. This is player 2 is kind of increasing their probability of playing heads, and this is player 1. And on this dimension, you have the value of the game, the payoff to player 1. And the only natural equilibrium is for both to randomize 50-50. It's just right here. It's conveniently looked by slicing the three-dimensional structure in this way, and you sort of see that it's got to be an equilibrium in the sense that player 1 could be moving along this curve, but as he does it, his payoffs would only drop, and so he's trying to maximize the value. He wouldn't do it, and conversely, player 2 can only traverse along this, but if he does that, the payoffs would only increase, and he's trying to minimize the value. So you get a stable point, which for obvious reasons is called a saddle point. So although there are general purpose procedures for finding a natural equilibrium, in particular in 2x2 games, we can use the Maxmin definition to find it directly in zero-sum games. And let's see how it happens in the game we'll call the penalty kick game. So in this game we have a penalty kicker and a goalie. It's a zero-sum game, and the goal of the kicker is to score a goal, and the goal of the goalie is to prevent it. And let's assume that they each have two strategies: kick to the left and kick to the right for the kicker, and jump to the left and jump to the right for the goalie. The payoffs will be each of those will determine a probability of the kicker scoring a goal, and we'll have that probability being the payoff, the value of the game. That is the payoff to player 1, and therefore minus the payoff to player 2, namely the goalie. And so here they are. So for example, if the kicker kicks left and the goalie guesses correctly and jump left also, then the goalie has not too bad a chance of stopping the shot, namely probability 0.4. If he jumps to the wrong side, his probability of stopping it is much lower, it's 0.2. Similarly, if the kicker decides to kick to the right, if the goalie guesses wrong, his probability is low, even lower than if he guessed wrong in the other case. And if he guesses right, his probability is higher, although not quite as high as that had he guessed right in the left case. So he's better at stopping shots when the kicker kicks to the left. So how does the kicker maximize his minimum? That's what we're after. So here's the expression, right? We want the Maxmin value of the following. So they each have some mixed strategy of playing left and right with some probability. So S1L is the probability that the kicker kicks to the left, and S2L is the probability that the goalie jumps to the left. And as we saw, in that case, the value is 0.6. And similarly, the value is 0.8 isn't if we end up in this situation, 0.9 and 0.7 in these situations. Okay, so this is the expression that we somehow need to compute. So what is the minimum that the kicker should keep in mind? So the kicker says, I'm going to play my strategy S1. whatever it is. When I play it, player 2 is going to play S2 so as to minimize my payoff. So let me write down this entire expression, and I'm just, this is simply copying it over, replacing expressions such as S1R by 1 minus S1L. That's all it's doing. And the same for S2R. And so we have, this is our expression, and player 1 is saying to himself, what would player 2 do if I were to play my strategy S1? And this is simply rearranging the terms, nothing else going on here, as a function of S2L. Because player 1 says, I'm going to pick S1. What would S2's be best response, namely its minimum? And so this is arranging it as a function of S2's strategy. And now all that remains is to look for the minimum of the strategy. And the minimum is taken by taking the first derivative with respect to S2, holding S1 as a constant. And so we have this expression. And then we solve for S1, and we get that S1 of L is a half. And therefore S1 of R is a half as well. And so by this Maxmin calculation, we see that the kicker figures out that in equilibrium, they'd better randomize half-half between left and right. What does the goalie figure out? Well, he's trying to minimize the kicker's maximum, right? That's one way to look at it. He's doing the min-max strategy. And so here's the min-max strategy for player 2. Just writing it down. And as before, we'll simply rewrite S1 of R as 1 minus S1 of L and so on for S2 of R. And we'll rearrange the term, this time as a function of S1 of L, because player 2 is saying, player 2 says player 1 is whatever I choose, namely S2, player 1 will want to best respond, namely to maximize. So let me write it down as a function of S1's choice, and now figure out what the maximum would be. Well, here's the maximum, and when you solve for L2 now, you get that the randomization in equilibrium for S2 is, for player 2 is 1/4 and 3/4. So this illustrates how we can use the Maxmin theorem to actually compute the Nash equilibrium in zero-sum games, at least in 2x2 games. In general, we can use the min-max theorem to compute the equilibria of zero-sum games, and we do it by simply laying out a linear program that captures the game. And here it is. So U1 star is going to be the value of the game, that is the payoff to player 1 in equilibrium. And so we're going to specify from player's 2 point of view. We could have done it the other way around also. So what player 2 is saying is simply, says, for each of the actions of player 1, each action that player 1 might consider, I want to find a mixed strategy S2. So here's my mixed strategy S2. It will look at all my pure strategies K and make sure that the probability, that's the probability distribution over those. They sum to 1 and they're non-negative. So what I'd like to do is that the best response to my strategy by player 1 for any of these actions will never exceed this value of the game, because I'm trying to minimize it. So I'm going to find the lowest U that has a property that player 1 doesn't have a profitable deviation by any of his pure strategies. So when I look at the payoff for player 2, when I play A2K and he plays A1J, that J that I'm considering right now, and I multiply the probability of, in my mixed strategy, playing A2K, I don't want that other player 1, to have a profitable deviation. So it's got to be that his expected payoff will be no greater than the value U1 star. So clearly this is a correct formulation of the game, and it is a linear program. As we know, linear programs are efficiently solvable, in theory by a interior method that is provably polynomial, in practice by procedures that are worst case exponential, but in practice work well.
This video will explain to you the intuition behind a new game theoretic solution concept called correlated equilibrium. Let's think again about the battle of the sexes game, and let's think about its Nash equilibria. Remember, there's a Nash equilibrium where both players play B. There's a Nash equilibrium where both players play F. And there's another Nash equilibrium where both players randomize according to these probabilities. And that means that all 4 of the outcomes can happen. So both of these outcomes can happen, but these ones can happen as well. Now, let's think about intuitively what makes the most sense to us about the battle of the sexes. It's really that this outcome would happen half the time, and this outcome would happen half the time. Right? If you and your partner really did have different preferences about what to do and you wanted to be together, you would work it out where you each win half the time. And something that might have struck you about Battle of the Sexes is it doesn't give us a way to say that that's a stable outcome. And the reason why we don't say it's stable is that if both of these things can happen, then both players have to be playing mixed strategies with full support, and that means the miscoordination actions have to be possible as well. Well, here's another example that we can think about that will give us some intuition for why what's really going on here and how we can do something about it. So this is the traffic game. So this models a situation where 2 cars are coming together to an intersection, and they have to decide whether to wait for the other person to go through first or whether to just go through. Well, if one of them goes and the other one waits, then the one that goes gets the most utility, and the one that waits gets a bit less utility. If they both wait, they're both strictly less happy because they both waited and they still have to decide what to do. If they both go, the worst of all things happens because they crash into each other. So in total, we have 2 pure strategy equilibria that are, again, asymmetric, kind of like in Battle of the Sexes. And of course, it's also possible to have a mixed strategy equilibrium here. But let's think about what would really happen in the world when we have this kind of situation where we have an intersection and there's the possibility the cars might collide. What we really do is we have a traffic light. And let's think about what a traffic light means game theoretically. It's a fair randomizing device that recommends actions to the agents. It tells one of them to go, it tells the other one to wait, and it's fair in the sense that at different times it makes different recommendations. Well, the benefits here are that the negative payoff outcomes are completely avoided. We can achieve something fair, and in general, although not in this example, it's possible to end up with a sum of social welfare that exceeds that can be achieved in any Nash equilibrium. Well, we can use the same idea to achieve the fair outcome in the Battle of the Sexes game. So we could have a situation where the husband and wife flip a coin, and depending on how the coin comes up, they go together either to the ballet or to the football. Well, this is essentially the idea of a correlated equilibrium. A correlated equilibrium is a randomized assignment of action recommendations to the agents such that everybody wants to follow the action recommendations. So we have some randomizing device that tells me B some of the time and F some of the time. And and in a correlated way, potentially correlated way, tells you B some of the time and tells you F some of the time. So flipping a coin, where if it's heads, we both get the recommendation B, if it's tails, we both get the recommendation F, is a randomizing device like this, although it's possible for it to be more complicated. And in principle, if it comes up heads and we understand that to mean that we're both getting the recommendation B, this doesn't compel us both to go to the ballet. We still get to freely decide how to interpret that recommendation. But it's a correlated equilibrium if neither of us would want to deviate from the recommendation. And you can see in this example with Battle of the Sexes that indeed neither of us would want to deviate. Because if the other one is following the recommendation and I deviate, then I'm just going to get a payoff of 0 instead of getting a positive payoff. So a correlated equilibrium is any such randomized assignment of these possibly correlated action recommendations that leaves nobody wanting to deviate. It's a generalization of the idea of Nash equilibrium, because if these action recommendations are not correlated at all, then we just get back to mixed strategies like we had before. So we can capture any Nash equilibrium this way. But we can also get new things like we've just seen. So it's this strict kind of weakening of the concept of Nash equilibrium. It includes more things. And it can get us these kinds of nice, fair outcomes.